Hello, physics! It's me, Mr. Alexander. And today we didn't get a chance to finish this problem in class. We started it in the warm-up. This is problem 58, the at-sea rescue. It's in your textbook. I forget what page it's on, but it's in the end of chapter 6. And this is where you have an airplane flying purely horizontal at 125 kilometers an hour, dropping a box of supplies that's supposed to land right next to some survivors. Two questions about this. One is, how many seconds before the plane is directly overhead should the box be dropped? So basically this is asking, if this is where we're trying to drop the supplies, here's our plane, where should the plane be? Should it be here, there? Where should it be so that the supplies basically do this and land on the target? That's the question. So we want to know, how long does this take? What is delta t? And also for part B, it's asking, how far away should we be? How far should this distance be? So really this is a question. The first question is, how long does it take to fall from 1,001 meters to 0 meters? There's an easier way to think about that, and that is to think about how long it would take for an object to just fall straight down. That's really what this problem is. So that's what we're going to solve for. We already have all the givens. We already did the dimensional analysis. And so now I'm just going to go into the equation. So think back to those 4 equations that we put in your equation chart. Out of those, the only one that will work is this one. The change in position, the y position, since we're talking about free fall, equals VIY times t for time plus 1/2 AYT squared. Actually, I think in your equation chart we wrote delta t's. Doesn't matter. So, with this, we can think about some things from our givens to make this equation even simpler and actually turn it into this really cool equation that we can always use to solve free fall problems. So I'm going to show you how to do that right now. Okay, delta y is a number. It's the change in height. It's negative 1,001 meters. So we're going to leave that alone just for now. But I want to show you which one of these terms becomes 0 and makes life simpler. So let's see. This one right here, the initial velocity in the y direction, is going to be a special term because our plane is flying purely horizontal, which means when the package gets dropped, it's not moving in the y direction. So that means something. That means that this VIY is 0, which means this whole term goes away. So this becomes 0, and now we really just have 1/2 AY delta t squared. Now, if the goal here is to solve for delta t, then we just need to isolate delta t and get everything else to the other side. So watch this. That's what I'm going to do. I'm going to divide. Hopefully this is the good pen. Nope. I'm going to divide. Basically, I'm going to multiply by the reciprocal here. So we'll divide by 1/2 AY on both sides. A little y, there we go. And what we end up with is this stuff all goes away, and we're left with delta t squared over here, and over here, over this 1/2, the 2 moves to the numerator. We get 2 delta y over AY. Solving for delta t, we would take the square root of both sides. So here I'll do that. And rewrite the equation over here. Now we're going to have delta t, and I'm flipping sides here, delta t equals the square root of 2 delta y all over AY. This equation you can always use for any free fall problem where the object starts at a y velocity of 0. So the object can be moving horizontally, however fast it wants to go, or it could just be sitting still, not moving at all. As long as those are the cases, either of those, you can use this equation to figure out t. It's a beautiful little equation. Pretty simple. Just plug in the change in height and the acceleration, and this is pretty much, unless you're on a different planet, 9.8 meters per second squared. So, here we go. Let's plug it in. This is going to be 2. This is going to be negative 1,001 meters. This is going to be negative 9.8 let's see, some units go away. These meters go away. The seconds, since it's in the denominator of the denominator, it's going to move back up to the top. And then we're going to take the square root of it. And since it's squared, and that's the square root, it's just going to become seconds. And the answer is 14.3 seconds. So that, ladies and gents, that is delta t. Now, since we know what delta t is, we can use that to figure out how far away we need to be. Hello. Still with me? So I'll do that right over here, and we're going to use this. This is part B. And for part B, this is actually even simpler. For this one, I didn't write the equation yet, but think about it. For constant horizontal velocity, which is what we have here, right? The object is going to keep moving at the same velocity as it falls down. We can use a special equation. What is that equation? What does it mean when there's constant horizontal velocity? Is there acceleration? No, there is not. And therefore, we can use this very simple constant velocity equation, which says that Vx is equal to the change in position over the change in time. Well, guess what? What are we looking for? Which one? See how I did that? Ooh. We're looking for this. So we want to isolate for that. So I'm going to move delta t to the other side, and I'm going to get delta x equals Vx times delta t. Do we know the initial x velocity? Why, yes. Yes, we do. Do we know the change in time? Yes. Yes, we do. Can we solve this? Yes, we can. See? Say puede. So here we go. Delta x equals 34.7 meters per second times 14.3 seconds. The seconds cancel out, and you end up with a number 497 meters. This is how far away you should be over here in order to drop this and have it land there. Now, how big is that? How many football fields is that? If you said 5, you're right. You'd want to be 5 football fields away if you were going this fast in order to have the object land on the right spot. By the way, 125 kilometers an hour is about 75 miles an hour. So think freeway speed if your mom or dad speeds a little bit. That's about how fast we're talking about. And dropping 1,000 meters is 1 kilometer, or about 0.6 miles, or probably about the distance from the Victory side of campus all the way up to Van Owen by the middle school. So if you were over Victory, flying towards the middle school at 1,000 meters at 75 miles an hour, and you dropped a package, it would land on Van Owen. There you go. Hope you enjoyed this. Have a good weekend. Your homework is going to be to watch this and then do a very similar problem, which is 59, and then do problem 60 using the range equation stuff that we learned in class today. So I hope you enjoy it. Hope it all makes sense. If you have any questions, you're more than welcome to on the Remind app, and I'll see you Tuesday.